Thank you very much. I'm really delighted and honoured to be invited to give the Denver Russell Memorial Lecture. I think Denver Russell might have found this lecture a surprising extrapolation of the work that he did. But I think what I hope is by the end of the lecture, I will have explained some of the links between astrobiology and applied microbiology, and some of these surprisingly strong links between these two areas of activity. Now, for those of you who may not have stumbled across astrobiology before, the definition of this area varies depending upon who you speak to. This is a NASA definition, the origin, evolution, distribution, and future of life in the universe. It's rather a mouthful. Sounds a bit like the life, universe, and everything. I think one can get caught up in human definitions, but scientifically what's interesting about this field is it seeks to understand life in its astronomical and planetary environment by addressing questions like, how did life originate on the Earth? How has it persisted for 3.5 billion years or more on the planetary crust? What is the future of life as the Earth develops? And I think one of the most profound questions in astrobiology, at least a question that interests the public and certainly the media, is there life elsewhere in the universe? It's often been said that it doesn't matter what the answer to this question is, either way it's terrifying. If there's no life elsewhere in the universe, then why have we spent the last 40,000 years building a civilization? For what purpose? Is it just so that we can be lonely in greater luxury? What is all this for? If there is life elsewhere in the universe, what is the nature of this other life? Is it simple microbial life, relatively simple microbial life? Or is there intelligent life? And if there is intelligent life, can we ever communicate with it? Or is it so far away that for all intents and purposes we are isolated? So either way, this is a profound question. 20 or 30 years ago, if you had said that you were a professor of astrobiology, people would have, your colleagues would have looked at you like you were insane. And certainly many of my colleagues still do. But there are good reasons why this subject has now entered into the mainstream of science. And if you have any interest in planetary sciences or space sciences, you'll probably recognize that one of the reasons for this is the discovery of diverse aqueous environments in the universe. I just want to begin this talk just by summarizing some of these recent discoveries to put into context why microbiology, and extremophile microbiology in particular, has become so important for planetary scientists and astronomers. Now, aqueous environments, as you'll understand, as microbiologists, of course, are important because we assume that liquid water is an essential requirement for all life, microbial and multicellular life. There's lots of sort of interesting science fiction discussions about the possibilities of things like liquid ammonia as an alternative solvent, but we have no empirical evidence that life can use alternative solvents other than water. So this is a reasonably conservative assumption to make, that life requires liquid water. But even with this conservative assumption, the discoveries over the last 20 years or so have been astonishing. For example, if we take the planet Mars, this is just a classic sort of vintage image of the surface of Mars taken in the 1990s by the Pathfinder spacecraft. It's a sort of image that you see on the internet, and it shows you what looks like a dead desert world. Mars is about half the size of the Earth, and in its early history, the core of the planet solidified, causing the magnetic field to shut down. So on the Earth is of sufficient size to maintain a primordial liquid core that generates a dynamo and a magnetic field that protects our atmosphere from being sputtered away by the solar wind. This is not the case on Mars. It's a much smaller planet. Most of the atmosphere was sputtered away when the magnetic field disappeared about 4 billion years ago. And as a result, the atmospheric pressure dropped. And today, it's at the triple point of water. So when we heat ice on the surface of Mars, it turns directly into gas. And that's why there are no sustained bodies of liquid water on the surface of Mars today. But there's very good evidence that conditions were very different in the past. This is an image of Jezero crater. It's a 50-kilometer diameter crater. This is the edge of the crater. The area here is about 50,000 square kilometers. And what you're looking at here is an ancient river coursing its way into this crater. And this is a delta deposit. This is a false color image. So the purple deposits are pyroxenes, which are found in volcanic rocks. The browns are olivines, which are found in volcanic rocks. And the green areas are clays that result from the interaction of rocks with water. So in other words, the weathering of rocks in water to generate clays. This is evidence for sustained liquid water on the surface of Mars about 4 billion years ago. And we don't know how long this lake lasted for, possibly something on the order of several million years, maybe longer. But here we have liquid water in contact with volcanic rocks. And of course, if you go to places like Iceland and other volcanic environments on the Earth, they are abundantly inhabited by microbial life. So the question is, was this environment habitable, and did it ever host life? And we don't know the answer to that, but this is, of course, a good reason to go and answer the question on Mars, simply because we have here an environment where we know there's liquid water. This is the Curiosity rover in Gale Crater, where it landed just over a year ago. This is the landing ellipse. It landed inside Gale Crater, and it drove off towards Mount Sharp. And within about a day or two of landing on Mars, the Curiosity rover observed these rocks on the surface of Mars. And if you drive up to these rocks and look at them close up, what you see are these conglomerates of pebbles and rounded rocks within these lithified sediments. And these are evidence of an ancient riverbed on the surface of Mars, where the pebbles have been rounded by water and then have formed sedimentary deposits that are then lithified, turned into rock, and are now exposed on the surface of Mars. Just further direct evidence on the surface of Mars for sustained liquid water on the surface of that planet. And if you drive towards Mount Sharp, this is a picture of Mount Sharp in the distance. These white dots show you an unconformity, lava on the top. And from orbit, these are clays and sulfates that, again, were formed in an ancient lake. The clays from the weathering of volcanic rock, the sulfates from salts that are found in lakes. So, in other words, another aqueous environment. If you drive up to Mount Sharp, in amongst these sediments, these are the sorts of images that come back. And this is really an astonishing image. This is the valves or laminations of ancient sediments laid down in a lake about 3.7, 3.8 billion years ago on the surface of Mars. If you found these on Earth, there would be little hesitation in thinking this was a habitat for life. Sustained liquid water in a giant lake, sediments being laid down over millions of years, the ideal habitat for microbial life. The question still remains, did these environments on the Earth, that were very similar to environments on Mars and very similar to environments on the Earth, ever host microbial life? And again, we, of course, at the moment don't know the answer to this question, but these findings of long-lived water bodies on other planets are driving astrobiology and have brought it into the empirical realm. Because the other thing we should point out here that is important is, even if these environments never had life, they may still have been habitable. If there was never an origin of life on Mars, for instance, we could imagine large bodies of liquid water that could have been completely sterile. This is a paradigm that's difficult for us to accept on the Earth. We rarely find lakes and rivers that are sterile, just because there are so many microorganisms on the Earth that as soon as a new habitat comes into existence, it gets very rapidly colonized. But if there was never an origin of life on Mars, it could be that these lakes never had life, but they were habitable. So we want to know, one, are these environments habitable? And secondly, could they have ever sustained life? Again, 20 or 30 years ago, if you had said, well, I'm going to go and look for liquid water habitats beyond the orbit of Mars in the depths of the solar system around the giant gas planets, people would have also thought you were crazy. But now we know that there are very large bodies of liquid water beyond Mars. Liquid water that is not sustained from solar heating, but rather from tidal forces buckling icy moons that melt the ice from internal heat. So on the left-hand side here, in the Jupiter system, this is Europa, a moon about the same size as our own moon, and you can see this very white surface that's made of ice and very few impact craters. That tells you that this is a very recent, geologically recent surface, maybe about 10 million years old. And we know that inside this moon, there is an ocean of liquid water that has about as much water as all of the Earth's oceans combined. And we know this because if you go to the airport, you'll know how you walk through a metal detector. And the way that works is you walk through a magnetic field. And if there's anything metal on you, that piece of metal, which is conductive, disturbs the magnetic field and generates an induced magnetic field that can then be picked up and sets off the alarm. The same thing with Europa. As it passes through Jupiter's giant magnetic field, it causes a perturbation in that magnetic field that tells us that there's something conductive inside that moon. And based on the bulk density of that moon that we can measure by gravitational measurements and looking at the orbit of that moon, we know that the only material that satisfies the data is salty water. And so there's also other evidence besides the magnetic measurements that I won't mention here. But the evidence for a liquid water ocean below the surface of Europa is now fairly solid. And the question is that ocean inhabited? Well, exploring that ocean is a priority for the European Space Agency and NASA that plan to send missions to sample the surface of that moon. But here we're really entering into the realms of extraterrestrial oceanography. And on the right-hand side is Enceladus, a moon about 500 kilometers in diameter that orbits Saturn, very small moon, a bit like Europa. It's got an icy surface, very few craters. And this is an image taken by the Cassini spacecraft showing you geysers erupting from the south pole of this moon that we now know are erupting from an ocean beneath the surface of the moon, using the same methodology as showing the ocean under the surface of Europa. We know this is coming from an ocean. And about 6 years ago, NASA was able to reorganize the Cassini mission to fly the Cassini spacecraft through these plumes to measure their composition. And you can read the papers, but this is just a table from one of the Nature papers that came out from this fly-through, showing you all the materials that were found in these plumes. As well as the water, we've got organics in there right up to C6, H6. So what we've got under the surface of this moon is a place where there's liquid water and a vast array of complex organic materials. And yet again, the question is this inhabited or is it even habitable? And we don't know the answer to that, but these are questions that can be empirically addressed over the coming decades. And one plan is to fly a spacecraft through these plumes and collect material, so Enceladus sample return, and bring that material back to the Earth and look and see what's in there and determine whether that ocean is habitable. And even beyond our own solar system, remarkable advances over the last 2 decades. I think this is possibly one of the most astonishing advances in astronomy and by implications astrobiology, which I've simply written down here as the search for a second Earth, an Earth analog planet around another star. About 10 years ago, the Kepler Space Telescope started looking for planets orbiting other stars, and particularly small rocky planets. So the way in which it does this is it looks at the way in which a planet passes in front of a star and blocks out some of the starlight, causing a reduction in the starlight, a dimming of that starlight. This is called the transit method. And using the transit method, you can look for small planets, rocky planets, orbiting other stars. And the first Earth-sized planet orbiting a star in the so-called habitable zone was Kepler 22b, which is about 1,000 light years away. And what astronomers are looking for are planets in the habitable zone. The habitable zone is a zone around a star where liquid water is stable at the surface of the planet. Okay, as I've showed you with Enceladus and Europa, we can get liquid water outside the habitable zone from tidal buckling from giant gravitational forces of giant gas planets. But an Earth analog planet is a planet within the habitable zone where you have liquid water at the surface. And since the Kepler Space Telescope began its mission, a vast number of these rocky Earth-like planets have been discovered. If you go onto Google and just put something like habitable exoplanets, you come up with these sorts of images, which are like Argos catalogues of habitable exoplanets. And I do think this is astonishing. I mean, if you'd said to someone 30 years ago, we're going to have catalogues of Earth-sized planets around other stars that we'll be able to look at and try and study whether they're habitable, that would have been an astonishing thing. In fact, with relevance to this building, if you told some of these Victorian engineers that we will be building telescopes to look for Earth-like planets around other stars, that they would have looked at you in disbelief. But this is the era we're now living in. And the next stage, which will happen in the next 10, 20 years, is to build telescopes that can look at the light being reflected or transmitted through the atmospheres of these planets and look for biosignature gases like oxygen or oxygen with methane and try and search for the biosignatures of life. So within the next 20 or 30 years, of course, we won't know whether there's life across the whole universe, but we'll have a pretty good idea based on the missions to Mars, missions to Enceladus and Europa, and these sorts of investigations about whether our local galactic neighborhood sustains any sort of life or whether there's any evidence for habitable conditions. And this is really just a very quick summary of where astrobiology is at the current time. And in order for this science to advance any further, it finds itself linked to extremophile microbiology to be able to assess these environments as being habitable or not. Oh yeah, I just put this in. If you take the data from the Kepler Space Telescope and you just do an estimate of the number of habitable planets in our own Milky Way, it's something like, here's just a typical quote, 8.8 billion habitable Earth-sized planets exist in the Milky Way galaxy. So there are about 200 billion stars in the Milky Way. If you take the Kepler Space Telescope data and you extrapolate it, about 8 billion habitable Earth-sized planets, which, whether it's 7 or 9 or 10 billion is really trivial detail. There's a lot of planets out there. And some people say, oh, how can you be an astrobiologist? You don't have anything to look at. And you sort of say, well, geoscientists seem happy with one planet. We have about 8 billion worlds to go and investigate. I think that's probably enough for anyone's career. But astrobiology has a rich history ahead of it, trying to figure out whether, in fact, the Earth is something completely unique or whether, in fact, these other planets host physical and chemical conditions that might be supportive, at least to the life that we understand. So, of course, this is the central question that drives all these missions. Are any of these places habitable? And we might define habitable as the ability to support the activity of at least one known organism, where activity is some basic metabolic state to maintain survival, or it could be reproduction, but at a minimum, some ability to use resources in an environment to maintain a viable cell. And we can list, and all of you, of course, are familiar with this, the sorts of things that we need for an organism to be active in an environment. We need the 6 principal CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Of course, we don't know whether this is universal, but at least all life on Earth, at a minimum, requires these 6 elements to build the major classes of macromolecules, so we'll make the assumption that's required. We need some other elements, depending upon the organism, such as iron, for example, and iron-sulfur clusters or cytochromes. We need liquid water. We've discussed a solvent. We assume it's liquid water, and that's one of the primary drivers of our search for habitable worlds elsewhere. A source of energy that could be light for photosynthesis, for phototrophy, or it could be organic compounds or inorganic compounds for heterotrophy or chemolithotrophy. And then finally, we need some suitable physical and chemical conditions. And this last one is where the intersection with extremophile microbiology occurs, because this is very important. We can imagine an environment that has all these other requirements, but not this. So, for example, imagine some hydrothermal vent that's at 300 degrees. There might be all 6 of these elements in that hydrothermal vent. There could be iron as well. If it's under high pressure in a deep ocean, it could still be liquid water. And there's energy there as well. There's inorganic compounds, there could be organic compounds, but it's above the upper temperature limit for life at 300 degrees. So from our understanding of life, it is not habitable. So one of the crucial things that astrobiologists are always interested in is what are the physical and chemical limits for life? Because that allows us to ask the question, do the physical and chemical limits that we observe, or the physical and chemical environments that we observe elsewhere, map within the boundary space of those physical and chemical conditions that we know will support life on Earth? One way in which we can depict this is in a simple 2-dimensional plot. So this is just a plot of all life on Earth surrounded by some sort of fence that is defined by physical and chemical extremes beyond which life cannot go. And so we can, if we have such a plot and we have real data for this, we can then, as I say, ask the question, does an extraterrestrial environment overlap with these conditions, and therefore is it potentially habitable, at least with respect to physical and chemical conditions? And this is, of course, not a 2-dimensional thing, it's an n-dimensional hyperspace of the whole range of physical and chemical conditions that define the limits for life. And I think the first attempt to do this was by Julian Wimpenny, who came up with this plot about 20 years ago. He never published it, but he frequently came to microbiology meetings and showed this plot. And I think Lewis Dartnell put it in a paper recently. And here he just took growth data for extremophiles, cultured extremophiles at pH, temperature, and salinity, and produced a sort of rather intriguing boot-shaped plot that I think was actually a sort of landmark little exercise in extremophile microbiology, simply because it was the first attempt to sort of plot in 3-dimensional space, 3 extremes, and to define the parameter space of life. One of my postdocs a couple of years ago decided we would redo this and collect the more recent data, so Jesse Harrison. And we gathered together the most robust data that we could find in the literature on prokaryotic growth at different extremes. Of course, there are many other extremes in the natural environment, but we were just focused on using microbes that have been grown under well-defined conditions in the laboratory. And we redid the exercise from Julian Wimpenny. This is actually the analogous plot of temperature, salinity, and pH. This is just shown from different angles just so you can see the three-dimensional plot. And each one of these shapes is an individual prokaryotic strain. You can actually see that the overall shape here, this boot shape, actually is quite similar to what Julian Wimpenny produced, just updated with some more recent strains growing at more extreme temperatures. And I don't want to go into this data in too much detail. For the sake of this talk, I just want to raise some general points. They show us, to begin with, an apparent absence of organisms exhibiting certain combined extremes. So in these plots, there's a lack of hyperthermophilic alkalophiles, a lack of hyperthermophilic halophiles, at least ones that have been cultured in the laboratory. And we can progress beyond this and produce new types of plots. So we went on and did temperature, salinity, and pressure, and temperature, pH, and pressure, and so on and so forth. And you can also look at these empty spaces and start listing organisms that do not exist within these empty spaces. And these plots, as I say, are of interest not just to microbiology, but also to astrobiologists trying to define the limits of life. So why the missing spaces? This is important. Is it because this is telling us something fundamental about a lack of ability to organisms to grow in these environments? And does it mean if we found these environments elsewhere beyond the Earth, we could define them as uninhabitable? I think the answer is obviously no, and I've listed some reasons here. We probably lack information on response of strains to single and multiple extremes. As I showed earlier, this is rather a limited study of 67 prokaryotic strains. And I think probably what we need is more data on individual strains that have been grown at the extremes where there are missing spaces in these plots to find out whether we can expand these plots into the empty regions. A lack of isolations from multiple extreme environments. So one of the interesting things that I think about this exercise is that it compels us to go to environments on the Earth and look for organisms that might be growing in these environments. For example, high pressure and high salinities, at least salinities well above seawater, are obviously not found in the deep oceans, but we might want to go and find continental sites where there's evaporated, briny water deep underground that's under high pressure and see if we can find organisms that will fill in these empty spaces. We might want to go to salty, high temperature springs and isolate more organisms to try and fill in the spaces here. So clearly there's field work that is motivated by these missing spaces. And then, of course, there's a question of, do organisms, are they unable to adapt to multiple extremes for physiological and or energetic reasons? Could it be that under certain combined extremes, too much energy is required to deal with these multiple extremes? It's just not biochemically possible to live under 4 great extremes imposed all at once. And that's a matter for biochemistry to try and unravel. There's very, very little data on microorganisms under multiple extremes that is systematic, that looks at different extremes imposed individually and together. One of the reasons why we did this work was because it was the beginning of a postdoc that Jesse Harrison was doing, and I'll come to some of his data in a second. There are some data in the literature looking at combined extremes, and what they show is that things are not necessarily as intuitive as you might think. You might think if you expose an organism to one extreme and then add another extreme, it's just additive. You need more energy to deal with 2 extremes. And this is, of course, not necessarily the case. This is a nice paper by Nichols et al., where they looked at the growth generation time of this microorganism here, Glacier cola, under optimum growth conditions, which was 15 degrees, and suboptimum growth temperature, which was 8 degrees, which is the cross plot here. And what you'll see is that when you grow this microorganism under suboptimal growth temperatures, its ability to tolerate a range of water activity stress is actually increased. The breadth of water activity stress tolerance is improved when you grow it at suboptimal temperatures. In other words, tolerance to one extreme has actually been improved by exposing it to another extreme. And that's counterintuitive, and the physiological and biochemical basis for this graph is not understood, but it would be interesting to know why it's the case. But it tells us that we can't just look at microbes under single extremes and then extrapolate conclusions about what might happen under multiple extreme environments. We actually have to do those experiments. This was some work that was done by my postdoc, Jesse Harrison, where we decided to take a polyextremophile, Halomonas hydrothermalis, and expose it to a range of extremes, salt stress, iron stress or iron deprivation, oxygen deprivation, and a range of temperatures, individually and combined, and look at the response of this organism to these different stress parameters. And again, I don't have time to go through all the data, I just want to pull out one point. And the point that was interesting was that when you expose this microorganism to iron starvation with oxygen stress, you find that the temperature, the effects of temperature are essentially removed across most conditions. In fact, only under one condition did stressing them with temperature have a statistically significant effect on growth. Under all other conditions, the temperature stress became irrelevant. And it may well be that in this case, the organism is using its energy supplies to try and maintain a minimal type of growth under iron and oxygen stress. And as a result, when you impose temperature stress, in fact, it doesn't have an effect on the organism, simply because it's growing so slowly anyway. What's the significance of this? Well, the significance is if you go to an environment and you see extreme temperatures, you're inclined to say, here's an extreme environment because it's at high temperature or low temperature. You might look, for example, context of this meeting, at a low temperature environment and say, well, this is an environment for psychrophiles. They must be cold adapted. But it's possible that if the organisms in those environments are being stressed by other things like lack of iron or lack of oxygen, in fact, the temperature of that environment becomes completely irrelevant. They're growing at a very low level. They just don't see the low temperature stress because they're dealing with other types of stress. And so I think what this sort of study shows us is that, again, we have to be careful looking at natural environments and drawing conclusions about what stresses microbes are exposed to just based on what we see of the physical and chemical environment. We actually have to do the experiments in the laboratory and look at combined stresses to understand what's really going on physiologically. And for the astrobiologist, this is important because you can't just go to a planet and say, oh, look, it's cold, it's got this environment and this environment, therefore these are the requirements for an organism to live in this environment. If you've got a multiple stress environment, it's not necessarily intuitive which of those stresses are important. So I've just listed at the beginning of my talk here just some conclusions. Studies at the absolute limits to single extremes. We need more of this to map the boundaries more effectively. We need more research into multiple stress natural environments, more research in field sites in the laboratory to look at life under extremes, different types of extremes, an expansion of studies to other stresses in combination for which there is a paucity of data, such as low oxygen or heavy metals, and then linking, for the astrobiologist at least, linking these data to data on environmental extremes. I want to move on just finally to one last thing in this lecture, which is to think about totally alien types of environment that we don't even see on the Earth. This is another thing that we've been looking at. So this is Mars, as I've explained earlier, and just to briefly explain the water history of Mars in about 1 minute, as quick as possible. In the early history of Mars, in the Noachian here, about 4 billion years ago, there was lots of liquid water on the surface of Mars. I showed you those images earlier. Today, in the Amazonian, the planet is dry and desiccated, but it passed through this phase in the middle here where there was a period of acid weathering. So there's very little water on Mars. The water that existed mixed with sulfur dioxide from volcanoes and produced sulfuric acid. And that sulfuric acid weathered the Martian rocks and produced lots of sulfate minerals. This is very different from the Earth, where most of our briny environments have sodium and chlorine in sodium chloride, like our oceans. But on Mars, many of the minerals are dominated by these sulfates. And this is Meridiani Planum, which is one area on Mars that has these sulfate salts. This is just jarosite that was measured by the Opportunity rover. And all over Mars, we find these sulfate salts. There may even be liquid water on Mars today. These are intriguing images taken from orbit, and you can see these brown streaks that form seasonally on the surface of Mars that seem to come out from the subsurface. And even though the pressure on the surface of Mars today is at the triple point, there's no possibility of sustained liquid water on the surface of Mars, there may still be briny water seeping out from the subsurface and then just evaporating when it comes to the surface. So there's some compelling evidence for liquid water on present-day Mars. And we can model what those waters contain based on what we know from orbit and what we know of the geology of that environment. And one question we might ask ourselves is, were these or are these Martian briny environments habitable? We know that briny environments on the Earth are habitable. So these salterns that are inhabited by these archaea that produce these nice rich carotenoid red and orange colors. Most of these brines on Earth are dominated by monovalent ions, sodium and chloride, and that's a result of the geological history of our planet, where the oceans have been sustained over billions of years, and so we end up with these brines made of sodium chloride, and we know that these are often densely populated by microorganisms. But on Mars, the acid weathering of this basalt rock, as I mentioned earlier, results in very different geochemistries. Brines dominated by magnesium and iron sulfates. We might ask ourselves, could these have been habitable? So we did some experiments where we generated Martian brines in the laboratory. We took the modeling data and the orbital data, and we made these brines, and we gave our microbes in there everything else they needed, like a rich nutrient source, moderate temperature. We did this under aerobic and anaerobic conditions because we only wanted to stress them with the geochemistry of the brine, but give them everything else that they needed. And of course, you don't know what grows in there by definition because these are new brines, so we inoculated them with every reasonable and conceivable inoculum that we thought might have organisms that could grow in these brines. So we took inocula from salty environments. We used soils, just because soils have lots of different salt and physical and chemical gradients of very diverse organisms. And we even did the sort of Bass-Becking thing of putting these things outside and leaving them to the atmosphere for 4 months, so using the terrestrial atmosphere as an inoculum, and so trying to give the maximum possibility of these brines to be colonized by something that could grow in these salts. And we also have various controls that we use to separate out the individual extremes. This is probably the most useless slide in my whole talk, but yeah, it is completely useless. But for those of you who like geochemistry, these are the sulfate concentrations here. Anyway, you can't really see them in here as well. But the sulfate concentrations are very, very high, and what distinguishes these brines are these high sulfate concentrations. So we can do all the things that, of course, microbiologists do, which is to grow the microbes, we can stay in them, we can do growth curves. And the criterion that we use for successful habitability of these brines is the ability of microorganisms to reproduce in these brines. So we just do growth curves of the communities in these brines, and if we see an increase in cell numbers, we define that as habitable. And we produce two different types of brines. We produce brines that are very early stage brines, which are brines that are very dilute, and then brines at a late stage where they've been evaporated and allowed to produce very concentrated brines. We can look at the microbial community compositions. Again, in the interest of time, I don't want to say anything other than the brines are inhabited by unique microbial communities. This is a typical sodium chloride inhabited brine using our inoculum. You can see this sort of classic carotenoid-rich archaeal diversity in here. And what we find are these sort of unique microbial communities growing in these Martian brines. What's fun about this, I mean, scientifically it's interesting because now we have a brine community living in this Martian brine that we can start asking questions like how does it live in high sulfate concentrations? What sort of metabolisms does it have? There's also a bit of fun in here because this brine, there's no known terrestrial analog for this on planet Earth. We don't know of a natural environment, and yet we know this exists on Mars. So we've got these flasks in our lab of alien geochemistries that don't exist on the Earth with microbial communities in them, and we're looking at the structure. Of course, we don't know whether there's ever life on Mars, but this is great fun to do this work. Anyway, what's the important thing? Well, we can plot these habitability of these brines. So what I've done is plotted pH here against water activity. And what you can see here is the red line here, which is the currently acknowledged lower limit to water activity. And the reason why we've plotted against water activity is because that's one of the defining limits to life in brines on the Earth. Okay, so saturated salt is 0.75 water activity. So it would seem a reasonable starting point to ask the question, does water activity determine the habitability of Martian brines as it does for terrestrial brines? And you can see the green circles here are brines, Martian brines that are habitable and have communities in. The red circles are Martian brines that were not able to sustain any growth, at least from the inocular that we used. Okay, that's not to say they could never sustain growth. That's a necessary limit of the experiments. But at least using all the inocular we use, we could not get growth. And these lines here depict the evaporative sequence. So this is the dilute brine, and this is the highly concentrated brine. And this is the natural evaporative sequence that occurs on Mars when these things evaporate and go from dilute to concentrated. And these squares are just natural environments on the Earth, and you can see how they fall either side of this water activity. So what we observe here is that we have uninhabitable Martian brines that are permissive for growth with respect to water activity, which is intriguing because it might suggest maybe there's something else in these brines that's stopping them from being habitable that is not water activity. And what could that be? Well, there's something very different between Earth brines and Martian brines. And one of the things that I mentioned was very different is that Martian brines contain lots of sulfate and magnesium and iron, which are multivalent ions that cause a high ionic strength, unlike terrestrial brines that are dominated by sodium and chlorine, that are monovalent ions. So we can instead do something different, which is to plot water activity on the y-axis here versus ionic strength, where ionic strength is a measure of sort of charge density in simple terms. Martian brines have a much higher charge density because of these multivalent ions like Mg2 plus and Fe2 plus, 3 plus, and sulfate 2 minus. If we do that, what we find is that all the Martian brines lie in a region of high ionic strength on the right-hand side here, and all the habitable ones lie in a region of low ionic strength on the left. And even more intriguingly, some of these brines actually make a transition from being habitable to uninhabitable as they go into a regime of higher ionic strength. So our working hypothesis that results from this work, and Mark Fox-Powell, who's my PhD student who's been doing this work, has just published this, is that on Mars, because we have brines have lots of multivalent ions, ionic strength becomes a limit to microbial growth, often at concentrations of brines where water activity is still permissive for growth. In other words, water activity dominates, at least as one of the major stresses for life in terrestrial brines. But in Martian brines, it's ionic strength, at least in some of these brines, that defines the limit to life. And if we step back and think about this from a geological history point of view, it links extremophile microbiology to the long-term geological history of a planet. So on the right-hand side, we have a planet where liquid water has been sustained for billions of years. It has not dissipated and reacted with gases to produce acid weathering. And we've got brines that, where they do exist, are dominated by sodium and chloride, in other words, monovalent ions, chloride-dominated brines. But on the left-hand side, a planet that was very similar to Earth in its early history, but because it was smaller, it lost most of its atmosphere, the water dissipated, and the water that remained reacted with sulfur dioxide, formed acid, and produced a planet where almost all the brines are dominated by these multivalent ions, or sulfate-dominated brines. And the consequences for life, of course, we don't know whether there was life ever here, but the consequences for habitability is that on the Earth, one of the major defining limits to life in brines is water activity, whereas on Mars, ionic strength instead is one of the major defining limits to life in these sulfate brines. So here we can see an example of how we can link the geological history of a planet to extremophile microbiology and understanding the limits to life. And it's just, I think, a good example of why extremophile microbiology is so important to astrobiology. And just to reiterate, because it's just an important point to emphasize, we still don't know whether there's any life on Mars or not. But what I think is interesting about this sort of exercise is it demonstrates how astrobiology, even if we never find life on another planet, I think one of the wonderful things about astrobiology is it provides us with a way to look at things from a slightly different perspective. The idea that water activity is a limit to life in brines is just taken for granted. You don't really necessarily question why it's the case. It just is. Brines have low water activity, saturated NaCl 0.75. We don't really think about whether that's something unique to Earth. It's just a necessary physical reality of brines. But astrobiology shows us that it isn't necessarily something that is unique, that is true with all planets. In fact, other planets may have environments where different extremes limit life or limit habitability. So by looking at other planets, regardless of whether there's life there or not, I think we get a new perspective on understanding what limits life on our own planet and what defines that n-dimensional boundary space of extreme conditions. This, just to mention, is a new instrument that we've recently built at Edinburgh that allows us to simulate environments on Mars and look at the geochemistry and microbiology. So we can flow fluids in here, and inside here we can have a Martian atmosphere, and we can take samples by going in through the top here and remove them from these pots without changing atmospheric conditions. So this is actually the first aqueous simulation facility that allows us to look at the habitability of alien geochemistries, and will allow us to explore these sorts of environments, these ancient aqueous environments on Mars in more detail. So just to conclude my talk, it remains to be seen whether there is life beyond Earth or not. However, there is now unequivocal evidence for aqueous environments beyond Earth that compel us to ask the question, were they ever habitable? Did they ever have life? So we're no longer speculating about habitable environments. We have real places to look at. If we want to assess these places as habitable, extremophile microbiology is what provides the empirical basis for looking at these environments and trying to assess whether they're worth exploring or whether they might have ever been habitable to life. And I think the areas that are useful are the need to develop our knowledge of the limits to life under extremes, particularly multiple extremes. Like I mentioned earlier, there's surprisingly little literature looking at multiple extremes in a systematic way. And we need to develop our knowledge of the physiological limits to life under stresses alien to Earth that may be found elsewhere. There are all sorts of stresses like particular types of ionizing radiation that have no relevance to the Earth at all, but do exist elsewhere. And the sulfate brines are an example of something that's rarely found on the Earth, but is common elsewhere. Then we'll be better placed to define whether extraterrestrial aqueous environments were ever habitable or not. So I'd like to finish off my talk by thanking my postdocs and PhD students that have overlapped with the work that I've described in this talk, and of course all the generous people that have provided funding in one way or another through the years for this research. And I'd like to thank the Society again for inviting me to give Denver Russell lecture. Thanks a lot.